Hello and welcome to our presentation. We are Team Hashbash, and today we're presenting our thread-safe Hashmap. I'm Tyler Hostler-Mathis, and today I'm presenting alongside Ashley Vogelweed, Chris Herrera, and David Flores.
We're going to start off with a quick introduction. So a hash map is one of the most frequently used data structures that uses a hash function to map a set of keys and values. It supports very fast updates and queries with an average time complexity of order 1. The standard hash maps used in software development today are designed to be sequential, so this brought up the question, can we make it faster through safe parallelization? Let's talk structure. So before we go into any details, we need to nail down how we define a concurrent hash map. Then, once we have our definition locked in, we'll move to our current accepted research in the field. And then, we'll move into our specific implementation and cover everything from usage to benchmark tests. And then finally, we'll wrap things up with our future plans and improvements for our project. Let's start with our definition of a concurrent hash map. Our development of a concurrent hash map is primarily focused around these three properties: simple, extensible, and correct. So for simple, we wanted to create an API that is easy to use for developers and supports idiomatic method calls from multiple threads. For extensible, we wanted to leave room for improvement on our underlying containers and our data structures. And for correct, we wanted it to be fully linearizable, with each method call having a strict linearization point.
For this slide, we're going to take a look at the research done. What were the experts doing? Before we began development, we needed to form a strong basis for the current work in the field. This ensured that we didn't take any dead-end paths with no true chances of payoff. We also wanted to see if we could find applicability to real-world problems that would benefit from a safe, parallelized hash table. We start with the weight-free hash map research paper. This paper explores a weight-free hash map with atomic operations. This weight-free design avoids deadlock and performance bottlenecks that accompany traditional blocking implementations, such as mutual exclusion locks. The hashmap structure is a multi-level array similar to a tree, and each position contains either a single node or an array of nodes. The experimental results proved the weight-free design to be 7 times faster than the traditional blocking design. Research for this one was conducted by our very own Professor Damian Dechev, Stephen Feldman, and Pierre Laborde at the University of Central Florida. The next paper we took a look at was lock-free parallel dynamic programming paper. This research paper describes the application of a thread-safe parallel hash map being used to solve common dynamic programming problems. It takes a top-down approach, allowing it to solve any type of dynamic problem. This research paper showed a strong use case for a parallel hash map to solve common problems such as knapsack and shortest path. Here, dynamic programming problems are solved using a lock-free shared hash table that randomizes the order in which the subproblems are computed. This paper was written by researchers from the University of Melbourne, Australia, Monash University of Australia, Universidad Politécnica de Madrid, and IMDEA software from Madrid, Spain.
Now that we've defined our hash map and talked about some prior research, let's take a look at our implementation. Our hash map provides a simple and intuitive API, allowing the user to instantiate and query with ease. Here you can see instantiation of a hash map that maps strings to integers, backed by our add-only lock-free linked list, more on that later, with a capacity of 10,007 elements. We then associate the key test with the value 100. Finally, we provide 2 examples of lookup. The get function returns a Boolean generic pair, which can be destructured on call. The Boolean value will be populated with the existence of the key, and the generic with the key's associated value. If the key does not exist, this will call the generic's default constructor. Our hash map provides a templating structure for key, value, container, and hash function. This allows the user to completely configure the behavior down to the underlying container. For an example, if the user would like to use a custom implementation of a thread-safe red-black tree, they could. If they would like to hash a custom type, they must override the STL hash function for that type. As seen in the screenshot to the left, our hash map simply makes calls out to the underlying container, and thus its correctness is directly defined by that of its containers. All of our provided containers have clearly defined linearization points, and thus are linearizable. It follows that our hash map is also linearizable. We will now take a look at our actual implementation of the hash map itself. We begin by defining this struct that we call an entry. The struct is very simple. It consists of a key and a value, and we overload the equals operator. We only compare equality on key, and this is very specific. We do this to support updates. If a user wants to update some element, for an example, they're mapping the word test to 5 and they want to now map test to 6, we want our find functions to correctly identify the element in the underlying container and update it. And we only care about the key, not the value. So we're going to match on key here. Moving forward, we template the hash map on key, value, container, and hash function. And note that this container, again, as discussed earlier in the presentation, can be completely overridden. Moving forward, to get a hashed index, it's very, very simple. We simply mod by the capacity. To construct a hash map, we just need to start the capacity at whatever the user provides and construct this vector, which is our actual container that is going to hold all of our custom containers with the given capacity. And our destructor is actually very simple. There's nothing fancy about it. We just simply need to call all of the destructors for the underlying containers, but that will be done implicitly by the compiler. Our put function is incredibly simple. It simply grabs an index from the key, goes to the corresponding location in the hash map, and adds a new typed entry with that key and corresponding value. The get function is equally as simple. Again, we are relying heavily on our underlying containers to do most of the heavy lifting here. We simply get an index, create a new typed entry, look for it in the hash map. If we find it, we will return true alongside the actual value. Otherwise, we will return false as well as a default constructed instance of the value. Removal, again, looks for an index and calls the remove function on a typed entry with the corresponding key.
Here we have a summary of benchmark tests between our hash map and STL on various thread counts ranging from 1 to 20. So STL, which is the C++ standard library, is represented by the pink dotted line on the graph. And here you can see that smaller capacities suffer on smaller thread counts, but they begin to excel with larger thread counts. And large capacities actually beat STL right off the bat. And this is actually expected since we do not currently implement dynamic sizing. But overall, we saw amazing results with our runtime from our concurrent hash map. And more notably, we see that utilizing 20 threads to insert 1 million elements into a hash map with 50,000 slots runs 8 times faster than the single-threaded STL implementation.
We will now explore how we actually went about benchmarking our hash map versus STL. You can see that we have a number of tests here. We have different capacity bases, different limits, and different amounts of threads to test on. This is a slightly later iteration of our benchmarks, so you will see some small inconsistencies, such as supporting removals. We did not support this in our graphs that we generated, and this is slightly flaky still. There are some segmentation faults that can occur. You can see we simply go through every single possible permutation and combination of these capacities, limits, and threads. We assign them, we create a new hash map, and we open up some threads, equivalent to the number of threads in the test, in placing some put and remove jobs, and then we join them. We simply time how long that takes. Then we print the results to standard out, but we are also going to print them out to a CSV file here in the data section. We'll take a look at STL, and you can see that we benchmark here as well with a very similar method, except for this time single-threaded, so we only need to test limits. We're going to start, insert all of our elements, and then end. We also write to a CSV file. Looking over at those CSV files in the data section, we can see we have just a bunch of data that's basically our runtime for each permutation. And then in the STL version, we also have some runtimes. Now that we've gone over the hash map, let's check out the containers that drive it. We focused on linked lists for their simplicity and relevancy to class discussion. Specifically, we focused on 2 implementations, lock-free and blocking. Our lock-free implementation does not currently support deletion, for reasons we will cover shortly. A deletion-aware version is in the works. Most importantly, this implementation is very fast. The blocking implementation utilizes hand-over-hand locking and supports deletion. Unfortunately, this has a negative linear relationship between thread count and runtime because of its heavy use of locks. We'll begin our exploration of the underlying containers here in the lockable linked list class. You can see that the very first thing we do is define this lockable node struct. This is very similar to your typical linked list node with one small difference. We now provide a new member of the form mutex that will take the place of a lock for each individual node. We then expose some wrappers that allow us to lock and unlock this mutex, and finally another abstraction layer that allows us to get the next item as well as lock it. This is useful for a few methods you'll see coming up in the future. We begin by instantiating our head to an empty node, and this will just keep us from making any null pointer dereferences later down the line and simplifies the code a little bit at the sake of a single extra node at the beginning. We also maintain a size in our linked list as we want the user to be able to query this whenever they would like. When we construct the linked list, it's very simple. We're going to instantiate cur size to 0, and our head gets defined here in its default member initialization. We also need to define a destructor in case our linked list goes out of scope at any time, as we need to move through every single element and dereference them to minimize dangling pointers and memory leaks. Moving forward, we do expose an endpoint to allow the user to retrieve the head of the linked list. Note that this is not thread safe, and anything that the user does outside of this program with their own code is not guaranteed to be thread safe. In terms of add, we have a very, very simplistic function. It's very similar to most addition functions you would see in a linked list. The only difference is we lock nodes as we move through them to ensure that no changes to the list happen when we don't expect them to. So you can see we start some mover node at the head and we lock it. And while we are not all the way done, we are going to move forwards. You can see this right here. We're going to unlock our current mover. We're going to move it to the next node after we get that next node and lock it, and then continue forward. So what this does is it has the effect of locking the next node before we grab it, so that we can ensure that no changes are happening to the list. We have our base case here, which states that if our mover's value is equal to the value we're searching for, then we're all good. We can go ahead and unlock everything that we're dealing with and return our actual value. We don't actually return it here. We simply assign it since the value is a reference and return false, stating that this element was not added to the linked list as it already existed. And then at the very end, you can see that we do a return true because this is implying that the element was actually added. And you can see we actually create a new node, a new lockable node. We unlock our current mover after assigning the mover's next pointer, increment our size, and return true. Remove is very similar, standard linked list things. We're going to lock our nodes, exact same logic you can see here as we move forward with the unlocking, hand over hand locking sort of style. The only difference here is that if we've reached the end, we're just simply going to unlock and return false. But if we actually found the node, we need to remove it. So we are going to check our next pointer. If the val equals it, we are going to tie our current mover to the next. This is basically cutting the element out of the linked list and reconfiguring the pointers properly. Then we unlock everything. We safely free this next memory now that it's not connected to anything, decrement our current size, and return true. Moving on to the find method, again, it's going to be very similar to our add and remove. We're going to traverse the entire linked list, locking hand over hand the entire time. But if we find the element we want, we're going to assign, again, this reference here to the value, unlock and return true. And if we don't find it, we're going to return false. To get the size, we just simply return our current size. Now we're going to take a step forward and take a look at the add-only lock-free linked list. This is different from the hand-over-hand locking implementation because it does not use any locks and utilizes compare and set to assert that the list is in the correct state that it expects. Similar things happen as before. We have a single node that's going to be the head that will be instantiated to some value and never removed so that we don't dereference null on traversals. And you can see that here in the constructor. We also have a copy constructor, which is useful for resizing vectors that rely on this substructure. It's not directly necessary for a lot of applications, but just in case, we do have a copy constructor. We do define a destructor, which does the exact same thing as your hand-over-hand locking version. We're just going to traverse the list and free everything so that we don't have any dangling pointers. Again, like before, we do expose the head of the linked list for anybody who wants to do checks. We use this often in our tests. And here's where things get interesting. Our add method is very, very different from the hand-over locking version. We're going to optimistically traverse the linked list, moving from node to node, just assuming that everything is going as we expect and nothing is being modified in the linked list by another thread. And once we get set up, because we found the node and it's time to actually insert our location, we have an expected reference, which is our current node, and a required reference, which is what we're trying to add. And we are going to tell our predecessor to compare and exchange current with toAdd. And note that we do connect our toAdd directly to current so that we are inserting the element properly. And if this succeeds, then we've done it. Our linked list was in the state that we expected it to be, and we can simply increment our size and return true. But if this fails, then we're just going to go right back up to the top, start our traversal again, and do it once more. This is very unlikely to fail, but if it does, we might need to retraverse the linked list. Find is very, very simple. We're simply going to move across the linked list. If we find the value, return it. Otherwise, return false. Now, this dump contents function you see here is an attempt at implementing dynamic sizing, and we will touch more on this later, but in a simple form, it will iterate through all the elements, add them to a vector, return that vector, and reset the entire linked list to an empty state. And finally, we can also return our size. From this implementation, it's clear to see why it's so fast. Our objects are very small. They're just pointers to nodes that only store a value and a next pointer. And this compare and exchange will rarely fail. There would have to be a lot of contention for nodes to be inserting directly after each other for the entire time.
We now present benchmark data for our blocking implementation, where we can see terrible performance as thread count increases, spiking at 4,000 milliseconds with 4 threads and 20,000 insertions.
On the contrary, our add-only lock-free implementation scales beautifully with thread count, taking less than 500 milliseconds to insert 20,000 elements with 4 threads.
We'd now like to discuss why deletion is so difficult. Consider the following scenario. We have a linked list with A pointing to B pointing to C, and thread 1 is currently traversing through node B. Thread 2 then removes node B and frees its memory. Thread 1 then attempts to move forward in the list, which triggers a use after free violation. To solve this issue, we explored implementing a rudimentary garbage collection system. There are several implementations out there, but the simplest is certainly reference counting. Each reference keeps a count of how many threads reference it, and we only allow frees when this number is 0. Now, here's where things get really interesting. This was our attempt at a full support lock-free linked list, meaning that we're also going to support deletion. As described before, we have a significant problem if some thread comes along and frees memory that a different thread is currently looking at, so we attempted to address this issue by reference counting. Each node is going to keep track of how many people are watching it, and then what we can do is when we try to actually free some reference, we are going to assert that this watcher's value is actually equal to 0. And if it's not, we will spin until it is. We have a few wrapper methods to help us, but we'll get to those later. We use the same property here where we create some head that's going to be empty, but in order to keep caps on both sides of the linked list so that we don't run into any dereferencing issues when we're specifically looking at these markable and watchable references, we are going to also create a node at the very back of the linked list. Our destructor is very similar to all of our previous linked lists. And now we get to the interesting function safe_delete. We're going to pass in some pointer to a node, and we're going to just basically spin until there are no watchers left. And once there are no watchers, we will delete it. Here we have our implementation of an internal find method, and here's where things start to get rather complicated. We are following the implementation discussed in class for a lock-free linked list, of course in C++ in this case though. We will traverse the linked list, and if we find any nodes that are marked, This means that they have been logically deleted in the linked list. So at this point, we are going to attempt a physical deletion by removing this node via a compare and exchange. And notice the entire way through this entire program, or specifically this method, we are watching these references that we are retrieving. And of course, we have to stop watching them if we're going to be returning out of the method. Once we've removed everything from the linked list, if we actually find our value, we are going to return a window to our predecessor and current, and this will be used throughout other method calls. And again, note that we do not stop watching predecessor or current. And this is talked about here in the comments. This must be cleaned up by the callee, meaning that we can't ensure that the people using this reference, because it's being returned, we can't ensure that that they won't be dereferencing it. So we ourselves cannot stop watching it, and that will be up to our callees to do. Here we can see our add method. We find the window that we're looking for, and we notice, if the item already exists, then we're good. We can just stop. We don't need to do anything fancy. However, we can now guarantee that the current is the tail, so we're going to attempt to link it in with a compare set. And you can see this happens right here. This is very similar to the add method you saw in the add only lock free linked list. The only difference is we now stop watching these nodes, and we have these marks. Since we're adding it in and we don't want it to be logically deleted, we're going to expect the marks to be false. Moving on to our removal function, we have very similar structure. We grab a predecessor and a current, and we are going to attempt to delete it. We're going to start with a logical deletion, meaning we are going to change this node's mark from false to true. You can see we have a compare and set here. If the logical deletion fails, then this means that the structure of the linked list changed while we were trying to mark this node. So we're going to need to retry. We're going to go all the way back up here, find our window, and do it again. If it's successful though, we're going to move forward and attempt a full physical deletion. Now, note that if the physical deletion doesn't work, that's okay, because all the way back up here in our internal implementation of find, we assert that we must delete these nodes if we have found any that are marked. And right here you can see our attempt to physically delete the node. And again, if was cut is true, then this means that we have deleted it. So we're going to try a safe deletion of this node. And find is very simple. It's just a wrapper method for our underlying version of find, where we can then return the value if it actually found it, and make sure to stop watching and clean up after ourselves. So let's talk about why this watching, stop watching, and safe deletion version of reference counting is not working. It is a classic instance of the ABA problem. If we look here, we try to assign our successor to current's next value, and whatever the reference is stored in that value. Now, we make a call out to this get and watch function, which is right up here. And the first thing that we do is increment the watchers on the node passed in. Then we're going to return the node. In between the time that we pass current next into this function, and we actually increment the watchers right here, current next could have already changed. And if current next has already changed, it could have been deleted. And if it were deleted, then we can assume that there might not have been any watchers on it yet, and it might have been actually fully freed. So this exposes us to a lot of problems, because this thread could think that it's looking at the true next value of current, when in reality it's not. And when we try to increment the watchers right here, we are now dereferencing null, not because the node we are looking at was not properly watched or the reference counting is broken, but simply because it's not the node that we thought it was. This is currently broken, and we are trying to think of a fix and work on a fix. Hopefully we can have this done by the end of the research paper cycle.
Although we are happy with the work that we have put forward so far, there's always more to be done. Let's talk about what our next steps look like. Removal. We decided to leave removals out because they significantly slow down the runtime due to the need for markable references, retraversal upon compare and swap failure, and reference counting. We also determined that most use cases do not require removals and rely mainly on insertions and lookups. However, Given more time and resources, we do want to implement removals in future iterations of the hash map. Dynamic sizing. For the time we had, dynamic sizing was very complex, but we do hope to implement it eventually. The implementation will have the resizing functionality take priority over all other tasks. Specifically, they will hijack the other threads in order to complete the resizing task. Scalability. In our current benchmark tests, we use 4 threads for our linked list and 8 threads for our thread-safe hash map. If we had more resources, we would like to test on more threads to get a true picture of our scalability to determine if there is potentially a point where parallelization may hinder performance.
I will now update the branch that we are observing to be our dynamic sizing branch. Although this implementation is not completely done, you can at least gain some insight into what we are attempting to do. We've defined this concept of an inverse counting semaphore in the following header. An inverse counting semaphore provides an extra method called strong acquire. The acquire method adds to count, the release method decrements from count, and strong acquire will simply wait until the count is equal to 0. It seems a bit backwards to tell acquires to add and releases to subtract, but when you consider what we are using this for, it starts to make sense. We want all of the threads that are currently doing work to add to the count, and when they are done, subtract from that count, so that when it's time to resize, we don't resize while other threads are doing work. Our resizing thread will wait on this strong acquire to finish, and once it does, we can be certain that there are no other threads currently doing work. You can see this here in the beginning of our resize method. We're going to tell our workers to call a strong acquire. This will hang until we are able to actually acquire. If we are the first resizer, then it's time to reset our underlying container. And again, this is not going to be an issue because if we're the first resizer and we just waited for all of the workers to finish working, then none of them will be relying on the current state of the hash map. You can see a little bit of debug here as we work on what is currently going on. We're also going to wait until we're done building the new container to do anything in the actual resize method. And then we have a provider consumer context here where we have a resize index that is shared between threads, and each thread will be continuously grabbing a new index to test. They will get the index, and if the index is greater than what we are currently testing and currently rehashing, then we will need to stop. So we are going to wait until we're done with all of our resizers and then set the resizing equal to false and break. Down here, you can see the use of the method we will talk about in the future here, not thread safe dump contents. This is basically dumping all of the contents from the underlying container into a vector. And then we can rehash these elements into the hash map. And just like that, we've resized the entire thing, and this resize method would work for multiple threads working at the same time. Moving forwards, you can see that the put method, the get, and the remove method still have the exact same logic as before. It's simply surrounded by a workers.acquire and a workers.released. And all of our methods now check. On addition, on puts, they will be checking the size. If the size would make us overflow from half of our current elements, it's time to trigger a resize because we can imply that we'll have a significant number of collisions at that point. We are going to exchange the capacity to twice its current size. We are going to copy our entire current hash map content into a buffer. And then we are going to set our flags, reset our resizers, and finally set resizing equal to true. This will immediately consume this thread into the resize function, and note that all other operations also get consumed into the resize function here. This means that we are effectively hijacking threads, and any thread that makes a request to a currently resizing hash map will start to contribute to that resizing effort until it's done, at which point they can resume the operations that they were told to initiate in the first place. Again, this is currently broken, and we are not sure why. We have a few tests that we can run on it, but those tests are only working from a single threaded context currently. They work not very often from a multi-threaded context, but they do work sometimes, which is implying that we have some race conditions that we just can't see yet. Hopefully we'll get this figured out, because dynamic resizing is a very important part of most hash maps, and supporting only a static capacity does limit our use cases. Although the idea ended up failing, it is still worth mentioning our attempt at a managed hash map. A managed hash map is simply a hash map where the user does not have to manage their own threads. They can simply make requests from a single threaded context, and the hash map will spin up threads in order to delegate the work properly. Unfortunately, we didn't consider that the overhead of spinning up a thread is actually higher than just simply inserting that element on a single thread would be. So this ends up being much, much slower in practice than any other implementations, including a single-threaded and sequential version. But you can see the basic idea here. We're going to acquire a lock on some thread count, spawn up a new thread to actually do our insertion, and detach it. And that's really all that there is to it. It ended up being, again, very slow in practice, but it's still an idea worth mentioning, as there are ways to improve it, such as instead of inserting a single element and spawning a new thread with that single element, we could support batched insertions where users provide a large batch of elements, and then we would spawn a thread for them to actually go ahead and do that batched insertion. We'll now jump into the Jupyter notebook that has driven all of the visualizations you've seen so far in this presentation. We start by importing pandas and matplotlib, and then we define some plotting functions. Here we have benchmark data for our add-only hash map, and then we move forward to see some benchmark data for a hash map that supports deletions. Although flaky, sometimes segfaulting, we were able to get some benchmark runs out to see their relative performance. You can see that as thread count increases, with a low capacity, our runtime stays about the same. But as our capacity begins to increase, our runtime starts to decrease. The managed hash map, the disaster that it was, has some very, very strange benchmark results, and honestly, interpretation of them is kind of futile. As we added threads, we saw absolutely no improvement in runtime. Moving forward to STL, we have a linear relationship as expected. Our add-only lock-free linked list was very, very quick with a log scaling factor on the threads. The lockable linked list, again, expected poor performance. And finally, we have here a version of a hash set, which was not talked about in the whole presentation, but it follows from a hash map very, very quickly. Here we can see the benchmark data plotting our hash map versus STL. And with that, we've reached the end of our presentation. Thank you so much for your time. If you have any questions, comments, or just want to chat about what we did, then please feel free to send an email to any of the emails you see listed below. Again, I'm Tyler Hostler-Mathis, and I worked with Ashley Vogelweed, David Flores, and Chris Herrera.